Okay, hello. Petr, are you here?
Yes.
Okay, great. So, dear colleagues, let's start our next seminar of Quantum Technology Center of Moscow State University. And today our speaker is Petr Siyushev from a group of Fedor Zhelezko in Ulm University. And he will talk us about a group for defects in diamonds for quantum networks. So please.
Okay, thank you very much, Konstantin. It's a big pleasure to speak for this audience. So I will share my screen. And I think before starting, I should maybe apologize that my talk might be not very smooth. Yesterday I had vaccination and doesn't feel myself very well, but I will try my best. So, okay, can you see my screen now?
Yeah.
Okay, perfect. Okay, I have started with this slide where the typical diamond with very familiar to everyone brilliant cut is placed onto the microwave sample holder for experiment. However, this is not a typical situation for us. The life is more prosaic and we work rather with the boring diamond plates like a piece of glasses. But they're synthetic and they contain very low number of the defects. So these are typically so-called electronic grade diamonds. And as I said, in contrast to the natural diamonds, the number of defects is very low there. Also, for diamond, it is known more than 500 optically active defects, which quite a lot of them are listed in this Bible for us. It's a book by Alexander Zaitsev, who has collected a lot of different diamond defects in this book. So also it is more than 500 defects are known, only about 24 of them are relatively well explored and structures understood. However, before coming to the diamond itself, I would like to say a few words about the kind of a motivation why we go to there. And actually, most of the experiment for quantum information processing and quantum communication were done with the either trapped atoms or ions. And up to now, the tools for cooling down, for storing these atoms or ions are very well developed and they are kind of sophisticated. And these systems are extremely good because of all of them are identical and they are well isolated from the environment. They provide very good control over the quantum states. And here you see, for example, a picture where atoms are trapped in an optical lattice. So you can distinguish them, you can address them separately and so on. However, such devices require usually quite complicated apparatus for cooling and storing them. And typically they are bulky and also requires ultra high vacuum. And when we talk about quantum technology, we also think about something more simple that we can implement in real life, something similar to the standard electronic components which are used for our computers, smartphones, and so on. And therefore, we would like to go to semiconductor technology or something similar to semiconductor technology. And if you compare those two pictures, you would also see some spots, but these spots are single defects in diamond crystal. Once you implant them, or once you create them by some other means, they are there forever. You can store them without any specific apparatuses because of they just intrinsically trapped in the crystal lattice. And those defects, as I said, can be just created by the implantation. You just shoot ions with the ion gun to the diamond placed in the vacuum chamber, and then do some specific post-implantation treatment, and you would have these defects. And some of them are atomically like system with a characterized levels. They are discrete, and of course for this you need to have a low interaction with collective effects. So therefore they should be placed, they should lie within band gap of the semiconductor. Particular diamond is good for this application because it has 5.5 electron volts band gap. Some of them also provide very good quantum control over the spin state. And if we talk about the quantum information processes, these systems are potentially scalable. Of course, not only diamond is a good host material, but also some other semiconductor candidates. For example, silicon carbide, another example of wide bandgap semiconductors, which right now extensively studied. Also, rare earth containing materials such as yttrium, aluminum garnet, for example, or others, and even typical semiconductors on gallium arsenide. However, up to now, diamond remains one of the leading contender, mainly because of it has quite unique defect, so-called nitrogen vacancy center. And this defect has, as I said, quite unique properties which make it very useful for quantum information processing, temperature sensing, magnetic sensing, even nanoscale NMR, electric sensing, and so on. So, but at the moment we are talking about quantum information processing. And I don't want to talk much about nitrogen vacancy center because of it's a separate topic, but I will just recap some main properties. It's good because of the spin of nitrogen vacancy center has a long coherence time even at room temperature. And it's especially good because of it can be easily optically initialized and read out. And also spin can be easily manipulated by the microwave field. So that makes it kind of very interesting system. And if you think about creating some quantum register based on nitrogen vacancy center, you can make, you can place several nitrogen vacancy centers in a diamond and make them talking to each other by magnetic dipole interaction. However, in this case, you need to place nitrogen vacancy centers very close to each other in the order of 10 nanometers. And that make this task is really challenging from the technological point of view, because of you somehow need to deterministically implant them with extremely high spatial resolution. So that's not a very simple way, and especially if you think about large quantum networks where qubits should be separated by large distances, this is also not suitable. In this case, you would like to have those qubits interacting by flying qubits, basically photons. And there was a brilliant experiment provided by Roland Hansen group in Delft, where they made entanglement between two remote NV centers placed in different crestats by means of two-photon interference. However, that time entanglement rate was in the order of 1 even per 10 minutes. Actually, this picture is already outdated, and recently they managed to improve their technique and reach Hertz entanglement rate, however, in expense of fidelities, which is also not very applicable to the real life. Okay, from here we know that if we want to make a large scalable quantum network, we need extremely good spin-photon interface for each node, and also long-lasting quantum memory to record the spin state, to to write basically the spin state while providing the entanglement between each pair of nodes, and then by swapping the entanglement you can distribute your entanglement from node A to Z. And actually Y and the center is not so suitable for this. The problem, the main problem is that the entanglement can be provided only by the coherent photons which are associated with the zero phonon line. Whereas for the nitrogen vacancy center, the most of the photons are associated with the phonon sideband, and only 4% of the total emission is in the zero phonon line. The next drawback is a strong spectral diffusion and spectral jumps, because of nitrogen vacancy center has a permanent dipole moment, and all surrounding charges, for example, electrons in surrounding traps, or if it's placed close to the surface in some surface states, fluctuate, and therefore via Stark shift, your spectral transitions are always wobbling around. And the next problem that nitrogen vacancy center has two different charge state, well, at least two different charge state. And while preparing any sequence, you always need to either initialize or probe your charge state before running. Otherwise, you might simply end up in another charge state, and your protocol, your single run will be useless. Okay, that motivates us. In principle, some of the problems can be tackled, like low collection efficiency of the photons. I have to say that diamond is has very high index of refraction, and due to this, just about 4% of the total photons can escape through the surface of the diamond. However, if we shape the diamond surface in a half sphere, like here, then in all direction we have rays striking the surface at the normal incidence angle, and therefore theoretically you can collect up to collect photons into almost 2 pi solid angle. That would allow you to increase the collection efficiency by a factor of almost 10, depending on the objective. So there are two common ways how to create it. For example, you can either polish the entire diamond in the form of half a sphere, like shown on this picture, where it's placed on the microwave waveguide, or you can use focused ion beam milling and directly manufacture your solid immersion lens at the point of interest in your diamond. And this method we kind of commonly use for all our low temperature experiments with diamond defects. However, other problems like spectral diffusion and different charge states, these are difficult to treat. That motivates us to search for other candidates, and recently there was an entire group of the defects found associated with the fourth group of periodic table, namely silicon, germanium, tin, and lead. And surprisingly, or maybe not surprisingly, all have similar or basically identical physical structure, where the impurity atom is aligned along the bond between two carbon atoms, and because of the atoms is pushing out these two carbon atoms, it creates so-called split vacancy configuration. And that's actually a very nice thing about these defects, because of it provides this 3D symmetry. I will talk about this a little bit later. Okay, first of all, what are so special about those defects? If we take a look at the normal photoluminescence spectrum of silicon vacancy center, for example, first of all, you will see extremely sharp and narrow zero phonon line. And with this zero phonon line, almost 70% of the photons is associated, whereas phonon sideband is kind of quite low. That's a especially striking feature compared to nitrogen vacancy center. And if you look at the other defects, for example, germanium, tin and recently lead, we would see all the time the same characteristic, very strong ZPL and very small amount of photons in photon sideband. So for the lead vacancy, I don't want to say that it was really observed, because there were two controversial papers which claim that they observed lead vacancy. However, the position of zero photon line was different in both publications. Therefore, this has to be still clarified. And okay, we have extremely strong zero photon line which can interact with our incident light. And what can we do with this? First of all, we can think of very simple experiments, the typical experiment which we do all the time. We place diamond in the base crestat, we shine the laser onto it, and then collect luminescence with the avalanche photodiode and reject the laser light with the long pass optical filter. If we now scan our laser across one of the electronic transition, as soon as we hit it, we excite the defect, and then we will have photons emitted in the photon sideband, which we detect with avalanche photodiode, and therefore we kind of reconstruct the transition through which laser is scanned. This is typically called photoluminescence excitation spectroscopy, or PLE. However, we can do a different thing. We can remove this filter and let laser light, together with the scattered light by the defect, impinge the avalanche photodiode. And then we would see slightly different signal. So you see, first of all, that this has dispersive shape. And the reason for this is the following. Besides the scattered photons directly at the electronic transition, we have also photons from the laser, which are reflected back from the diamond surface into the APD. And those photons interfere between each other and giving rise to this signal. If we sweep it, this shape would depend on the distance between the defect inside the diamond to the surface from where light is reflected. So, of course, depending on this distance, you can acquire different phase, and therefore this picture actually can have something like negative resonance, positive resonance, and everything in between, like, for example, on this picture. If we would look through the diamond, we would always have a negative peak. So we would have absorption. That's because of the scattered light is always out of phase with the incident light, and then single defects create shadow. Sorry? Do you have question?
Looks like not.
Okay, sorry. So then you would have a shadow in the transmitted light. Therefore, in the transmission, this is always an absorption peak, and this would be called extinction. This is not really extinction, but historically it also in most of the publication called extinction in the reflection. Also, it's probably not exactly correct. And what I wanted to say here is that you see that the contrast of this extinction is 15%. So it means that the light which was scattered by the defect is very efficient, so that it can interfere with a lot of laser photons coming back to your detection system. And if we compare this with the extinction on nitrogen vacancy center, this signal is really tiny. So we had a very hard task to observe even 2% of contrast with nitrogen vacancy center. Also, for this experiment, we made the seal around the nitrogen vacancy center, whereas for silicon vacancy center, it was just a reflection from the flat surface of the bulk diamond. Nothing special, and we easily could have 15%. I will go slightly to the different defect just because of it's a little bit bright. It has a high quantum yield compared to silicon vacancy. And in general, if we just take a look at the phonon sideband photons, there are not so much counts. So it's comparable to nitrogen-vacancy center, around 200 kilocounts per second. But if we remove the filter and sweep our laser again across the resonance, we would see a huge signal originated from this coherent scattering. This is dominating signal on top of the laser reflected photons. And surprisingly, we can actually see this center without any filter. We can remove the filter and still see quite decent signal just directly from this center. That allows us to place this emitter, this is a defect, inside the nanophotonic cavity, nanophotonic waveguide. And if you excite it from one end and measure transmission, you would see exactly this extinction by a single defect. So, and here you can already achieve 18%, which kind of indication of very strong light atom interaction. And also, please note that in this configuration, the defect is placed really close to the surface. And as I said, for nitrogen-vacancy center, you always have instability of spectral lines because of the strong Stark shift, and especially if it's placed close to the diamond surface, as here. And here we can see the line pretty easily and nicely without any specific treatment. Why is that? As I said, the defect possesses D3D symmetry, which means it also has inversion symmetry. So because it has inversion symmetry, there is no permanent dipole moment, and there is no linear Stark effect, only second order. And in this situation, if you sweep the laser across the resonance, you always see that the line is very stable over many sweeps, and this is extremely nice feature. Okay, I hope we are all convinced that the optical properties is very nice. And how about spin properties? For this, let's start with the energy level diagram for silicon vacancy center or any of this family, silicon vacancy, germanium vacancy, lead vacancy, and so on. All of them would have very similar structure. So the ground state and the excited state are represented by orbital doublets, which are split due to spin-orbit interaction. And if we would like to define a qubit, we would rather have something controllable than just two orbits split by, for example, for silicon vacancy 50 kHz. If we apply magnetic field, we split each orbital to the Zeeman sublevels, and then we can address them separately. So we can define the qubit. I have to say that all transitions are spin conserving, but only if your magnetic field is aligned along the principal axis of the defect. If you have a misalignment, then there is a spin flip. And that's what we can use for optical pumping. If we start with one particular state and excite it, after some time, we will end up in another state, which is reflected on this picture. So once you don't have fluorescence, once it dropped due to spin polarization, we can apply microwave field at these transitions. And then, as soon as it hit those two transitions in resonance, we recover population on both levels, and then we see this nice resonance, which is called optically detected magnetic resonance. However, you see that the resonance is not very narrow. It's around 2.5 megahertz. And let's take a look at the typical spin characteristic of this silicon vacancy center at around 2 Kelvin. So first of all, T1 is in the order of 5 milliseconds, which actually can be longer if you align magnetic field more precisely. So these parameters still can be tweaked. However, if we take a look at the coherence time, it's in the order of just 1 microsecond, which is quite low. And the pure dephasing time measured by Ramsey fringes is even lower, so around few hundred of nanoseconds. So what's the reason for such a poor spin properties? The reason is that, for example, for silicon vacancy, the orbital splitting matching is 50 gigahertz approximately. And in units of temperature, it corresponds to around 4 Kelvin, which means you have a maximum phonon occupation at this frequency. Therefore, direct phonon relaxation is a very efficient process. And it's scaled linear if your T is much larger than the splitting. However, if you go, if you drop your temperature below this splitting, then it starts to scale exponentially. And that's a way how to tackle this problem. So you either need to reduce your temperature or you need to do something with the splitting. So, and this what was successfully implemented by Mikhail Lukin group in Harvard. They used dilution refrigerator to cool down silicon vacancy center to 100 millikelvin, and then they managed to extend the coherence time to 10 milliseconds. Another approach was shown also by collaborators in Harvard by Mark Lonchar group and also a group in Cambridge, where they placed silicon vacancy center in a diamond cantilever and then apply some force to produce a strain. And this strain effectively acts as an increase of the spin orbital coupling. So you can engineer your spin orbital coupling, so to say, by applying some strain, and then you can also increase the dephasing time, which they were able to increase to 250 nanoseconds. Also, these are good methods. Utilizing of dilution refrigerator is a very expensive thing, whereas use of the cantilever and applying strain distort actually optical properties because of you distort the symmetry of the defect. However, the question is whether we really need to rely on electron spin as a quantum memory. And the answer is no, because we always have other spins, nuclear spins in diamond. There are typically about 1.1% of carbon-13 atoms in a crystal lattice, which correspond to the natural abundance of the carbon-13. And you can always find some carbon-13 in the vicinity of your electron spin of your silicon vacancy defect, for example. And if it's close, then you would have a hyperfine interaction and your each Zeeman level would be split further. And now if you scan your microwave frequency along these resonances, you would see this doublet. However, such a strong coupling is not very preferable for us because in this case, if you do any manipulation on the electron spin, due to strong coupling, you also introduce noise on the nuclear spin, and that would result in decoherence. That's actually not a good thing for implementation of the quantum memory. Therefore, we need to think about some other carbon-13 spins which are placed far away from the silicon vacancy center, that the coupling is minimal. And this is actually our strategy, how we would like to utilize this group 4 defects for quantum networks. So first of all, we just want to use one of those defects, only the spin-photon interface. Whereas nuclear spin will be used as a quantum memory. But before coming to this point, we need to initialize and read out our nuclear speeds. Unfortunately, there is no such a straightforward way as it was developed for nitrogen-vacancy center. And to understand how we do it, I would start with a kind of simple sketch of spin locking technique. Spin locking technique is started with the initialization of the electron spin by just laser optical pumping. And then using pi/2 microwave pulse, we flip the spin into equatorial plane. Then we apply a long microwave pulse with a 90-degree shift compared to the pi/2 pulse, which is called locking pulse. And then we start to rotate our spin around different axes. Basically, we constantly drive our spin that it sees all magnetic fluctuation constantly changing sign and then canceling each other. So then you can consider this as a decoupling pulse. And after some time, while you keep this spin driving, you can apply next pi/2 pulse, again with a 90-degree shift in respect to the locking pulse, and then you can read it out optically. So, as I said, this sequence leads to the decoupling from the magnetic noise, and if you vary the duration of the locking pulse, you would see some kind of characteristic decay. And this characteristic time T1, so T1 is the relaxation time in the rotating frame, basically. However, situation would change if the Rabi frequency of the locking pulse would match the Larmor frequency of nuclear speeds. In this case, we see the drop of the decay curve. Why is that? The reason is quite simple. Actually, in ordinary conditions, the hyperfine splitting for the nuclear spins are quite small compared to the splitting of the electronic states. And therefore, cross relaxation between those two systems is really negligible because of small spectral overlap. However, when we drive our electron spin with a certain Rabi frequency, we go into the dress state representation, and then splitting between the states would be provided by the Rabi frequency. If you match the Rabi frequency to the Larmor frequency, we bring two systems in resonance and allow cross relaxation. And that's why instead of decoupling, we simply lose the coherence. That happens if you have nuclear spin baths where coherence is lost. However, if we have relatively close nuclear spin to our silicon vacancy center, the situation would be slightly different. If we represent our states as a joint states between our silicon vacancy electron spin in a dressed representation, a dress state representation, and also nuclear spins, then we bring two states in resonance, and the system starts to evolve coherently between those two states. And that's what you see exactly on this curve. There is a nice oscillation coming instead of decay. Well, of course, there is a decay, but also this oscillation, which indicates the coupling of individual nuclear spin to the electron spin. And this oscillation is proportional to the orthogonal component of the hyperfine tensor, which we can define from fitting of this curve. Also, this way opens, this technique opens the way for polarization of nuclear spin, because of each time we go from one state to another, we also evolve to the different orientation of the nuclear spin. Therefore, going along this curve and stopping, choosing specific pulse, we can always polarize our nuclear spin. And also you can see that there is a difference between the decay curve when we are out of the resonance with Larmor frequency and when we in resonance with Larmor frequency. Therefore, we can visualize our Larmor precession by simply sweeping the Rabi frequency of the locking pulse. And that's what we actually do. We simply sweep our Rabi frequency of the locking pulse and visualize Larmor precession, which for this particular center was 2.1 megahertz, which correspond to approximately 0.2 Tesla. To prove that this is not an artifact, we of course change the magnetic field and see that it shifts together with the magnetic field. And from here, we can derive the slope and find the gyromagnetic ratio of this nuclear spin is 10.7 megahertz per Tesla, which coincides pretty well with the carbon-13 gyromagnetic ratio. So that's kind of logical because there are not so many other nuclear spins in the surroundings. Moreover, this technique can be also used to polarize actually the entire bath, because of each time when we evolve from one state to another, we can reinitialize our electron spin again to the plus state, and we will end up here, whereas all nucleus which have already opposite spin stay in this state and do not participate in this evolvement of the states. Therefore, this is also a cumulative process where we can polarize the spin best, and that's what we can see here, that the polarization is rising. And also, if we kind of prepare, depending on in which state we prepare initially our electron spin, either plus or minus, we evolve in a different direction. Therefore, we can repolarize our nuclear spin bath in one or another direction. And that's what we do at this point, and we see how it evolves. Also, as I said, we see the change in the luminescence from the defect depending on the polarization. And this, of course, can be used also for readout of the nuclear spin. And that's what we can demonstrate by, for example, simple nuclear magnetic resonance with this method. First, we polarize our nuclear spin by applying several of these sequences. Then we change the frequency of the RF pulse, and then we read out. And then we do it point by point, and at some certain position, we see the dip. And the dip is shifted away from the Larmor frequency because of we have a hyperfine coupling. And this shift is exactly defined by this hyperfine coupling to the electron spin. So we can even go further and also show that we can control nuclear spin by RF field and initialize it and read out. So we perform a Rabi oscillation on a single nuclear spin, again by applying several polarization pulses and then chopping the RF field, so increasing the duration all the time, and then reading it out, which results in such oscillations. Once we define the pi and pi over 2 pulse, we can again measure the spin echo decay for our nuclear spin, which results in approximately 5 milliseconds. And this is not a coincidence that our T1 time of the electron spin is also around 5 milliseconds. This is actually the main limitation for our electron spin, for our nuclear spin, for the coherence of our nuclear spin. Yeah, because of any noise produced by the electron would be reflected as a, for example, jump of the phase on the nuclear spin, and then we are limited. But as I said, in principle, this is not a strong limitation, because of if we align our magnetic field better, then we can prolong the T1 time of the electron spin, and therefore we can also prolong the coherence time of the nuclear spin. Still, I didn't say, but actually, we couldn't implement the high fidelity swap to the nuclear spins because of this this curve corresponding to the lock-in relaxation is just around 3 microseconds, whereas to flip the nuclear spin, we need around 4 microseconds. Therefore, we lose the fidelity. And in principle, for the experiment, it is highly desirable to prolong the coherence time of the electron spin to several tenths of microsecond at least. That's what not possible at around 2 Kelvin for silicon vacancy. However, if we go to other defects like tin vacancy center, we have larger spin orbital interaction and larger splitting between the orbitals. For example, for tin vacancy, we have already splitting of 850 gigahertz, which increase the splitting by a factor of 17, and at least we can prolong our coherence time to the order of several tenths of microsecond, at least 50 microseconds for sure. However, there are some problems at the moment which we are facing with fabrication of these centers because of the ions are larger compared to silicon or even germanium. And while shooting them into the diamond, you create much more damages. And these damages is something what you can't easily get rid of. Therefore, these also result in some dephasing of our optical transition, and this is typical ALE spectrum which we observe for tin vacancy center, which is in the order of 80 megahertz. Whereas Fourier transform limited line, this should be around 30 megahertz because of the lifetime is in the order of 5 nanoseconds. So this work is still in progress, and we hope to get some good results soon. However, at the moment, I can't present them to you. So with this, I came to the conclusion. I hope I convinced you that group 4 elements have very nice optical properties, and the system can be easily initialized, coherently controlled, and manipulated and read out. And the nuclear spin can be used as efficient quantum memory. However, we still need to increase the electron coherent time, and then we will be able to build the quantum repeater node at the temperatures of helium-4 cryostats and do not go to the millikelvin range. So this is a list of our collaborators who provide our precious diamonds. And now I would like to thank you all for your kind attention. Thank you very much.
Thank you. So, colleagues, have you any questions?
Hi, Petr.
Hello.
Well,
Hi. So, very nice talk. And so I would like to ask you, what's your opinion on realizing quantum network, including perhaps some small scale quantum register? What kind of color center would be the ideal candidate for that purpose?
If I understood you correctly, because of my connection was, I think, not so good, you
Okay.
asked which color center I would see as a good candidate for the quantum repeater node application. Was it right?
Yes, yes, including a small scale quantum register.
So as I said, for a quantum network, you need to have basically 2 key parameters. One is the high entanglement rate, And second, you need to have high fidelity entanglement. So it also means that your quantum memory should last quite long, especially if you talk about the quantum nodes separated by large distances. So if you, to provide entanglement between all these nodes, you need to wait certain time, and therefore you need to store the state on some quantum memory during this time. I think that nitrogen vacancy center in this case is kind of loosey system, because of you at the end you anyway need to incorporate it into the cavity. And that's what really hard, because there is a long history, I think already more than 20 years, where people are trying to put it into the cavity, and still it was not really successful, exactly because of all this problem with the charge, with the fluctuation, with the spectral diffusion and spectral jumps. You always need to do something special to pre-select it and so on, and then you lose time, then your entanglement rate drops. As you saw here, group 4 defects are kind of stable, and in this sense they provide very nice perspective if you put it into the cavities, because they would be stable, and then you can have high emission rates together with a high spectral stability. Your photons will be absolutely indistinguishable and so on, and then you can create quite high entanglement rate, which would be sufficient to implement the entanglement distribution. Also, if you go to the nuclear spin state as a memory, well, nuclear magneton is low compared to the electron magneton, and therefore it's not susceptible to the magnetic noise. So it should last for quite long time, and it was shown that, for example, for carbon-13 in diamond at low temperature, you can have it for seconds. Therefore, in principle, I would say tin vacancy would be a good candidate for that, because of you have all the properties like the optical properties like silicon vacancy, but at the same time you might have a longer coherence time for high fidelity swap of the state from the electron to nuclear spin. This is not only the system which I see as a good candidate, because of there are other centers, for example, so-called silicon vacancy in silicon carbide, which also insensitive to the charge fluctuation, but not because of its symmetry protected, like in the case of silicon vacancy or group 4 defects in general, but because of ground and excited states are fluctuating with exactly the same amount. This is just a coincidence, and therefore you don't have a spectral jumps, which is also very nice. Also, count rate for silicon vacancy, for silicon vacancy in silicon carbide is not very high. It is not too low compared to, for example, nitrogen vacancy center, but you can put already this system into the cavity, and probably you can also achieve high entanglement rate. Therefore, silicon carbide systems are also quite promising for this application. That's what I would answer in this case.
Okay. So I believe in the quantum repeater area, people want to achieve benchmark, which is entanglement generation rate. It's larger than the communication is time. So it's break even point. And will you be able to predict which color center will be the first one to win this benchmark?
Oh, that's I don't know. I don't know which color center would win this racetrack, but yeah, that's why many people are trying to explore different approaches. I don't have an answer to your question.
Okay. Okay. Anyway, thank you. Very nice work. a long time. Very nice work.
What was the question?
It wasn't a question. It was, he just said that it just you had very nice talk.
Thank you. Thank you.
Okay. I'm sorry, connection is not very good. Okay, colleagues, any other questions? Ranjit.
Thank you, Konstantin. Thank you for your talk. It's a very good talk. I have two questions. First one is, when you are saying optical effects, do you mean linear and non-linear optical effects or properties?
Well, in general, and did you say optical effects or optical defects?
Properties? Sorry, optical properties.
Well, by optical properties, I understand. Well, basically, I refer to the emission of the photons, because for entanglement, you usually need very specific photons. They should be indistinguishable. That you, if you want to create entanglement, you can't distinguish from which system you detect this photon by any means. And yeah, if you somehow can find out from which system it goes, either, for example, by frequency or mode or whatever, you won't create entanglement simply. That's the point. And I talk about good optical properties in the sense that the emission rate is very high. It's like for silicon vacancy family of the defects, and also that they are spectrally stable. They predominantly associated with zero phonon line, not with the phonon sideband, because of the phonon sideband associated only with incoherent photons. So that's what I'm talking in this.
Okay, what I meant when I asked this question, because you can achieve entanglement by using linear optics, beam splitter, and you can also achieve entanglement by using nonlinear optics. In nonlinear optics, you have wide range of type of entanglements, but in linear optics, so is very small. So in your case, whether you are using chi1 or chi2, so this I meant these two things.
Okay, I see. No, here I just meant purely linear optics entanglement.
Okay.
In general, you can think about some different stuff, and actually it was also shown recently in a group of Mikhail Lukin, where they had two silicon vacancy centers placed in one cavity. And in this cavity, you can provide coupling between those defects just by quantum QKD. So, and there you can indeed use some non-linearities on a single defect to provide the entanglement.
Thank you. Last question. What about noise level? So can you do like your operations very efficiently, or you have issues with the noise level?
There is always issue with the noise level, and the noise level is component many points. For example, in preparation of the spin state, in preparation of the emission of the photons associated with some background from the diamond crystal. Yes, there is always some ways how to properly engineer your system. And for example, if we talk about some spin noise or whatever, you always can utilize some specific tools like dynamical decoupling to minimize this noise and so on.
Okay, thank you.
But for if we're talking about the noise for entanglement, the optical entanglement, we kind of rely on the heralding of the entanglement. Therefore, we can discard the events which are not associated with the entanglement itself.
Okay. Thank you.
Thank you.
Other questions? Okay, I have a question. As I understand, you said that it's really good candidates for quantum network, but up to now, no distant entanglement have been demonstrated. So what is the, or not? Okay.
Long distance entanglement was demonstrated. For example, I already showed one experiment with nitrogen vacancy centers that was done in Delft. And
yes. Nitrogen, yes, but I mean group 4 defects.
Group, yeah, okay, yeah.
It wasn't demonstrated. So what's the main problem? What's the main for demonstration disentanglement between silicon vacancy and our count?
I think up to now it was quite challenging to have a long quantum memory. And different people use different approaches. For example, we bet, so to say, on nuclear spins, and we pursue this way. And our collaborator and competitors in Harvard, in Michael Lukin's group, they use dilution refrigerator, and I think they are quite close to demonstrate it, actually. So because of they really managed to prolong the coherence time really to tens of milliseconds, and there are some technical challenges associated with the control of the electron spin by the microwave field, especially in the dilution refrigerator, where cooling power is really low. It's compared to, for example, normal helium-4 cryostat. It's these are orders of magnitude difference usually, and you can't apply the same amount of microwave power to make, for example, fast operations. But these are just technical questions, and this is a matter of time when they are solved and the entanglement will be demonstrated.
Okay. So, any other questions? Okay, I have one more question. If we compare the properties of these centers in the application of just a single photon source, so which one may be better? Silicon vacancy, other? I mean, for example, for quantum cryptography application or for linear optical quantum computing, for this application.
As far as I understand, for heralded single photon sources, it's still kind of problematic that you have relatively low photon emission rate. If I'm correct, maybe I'm wrong, and it was solved already. And in this sense, also the techniques might be more straightforward for the linear optics and the single photon sources. I still believe that these systems based on the memories is more kind of universal. But to say which system is better, well, all of them under investigation, it's kind of hard, speculative.
Okay.
Thing.
Okay. So, if there are no more questions, okay, thank you for a very interesting talk. So, thank you, and see all of you in our next seminars.
Thank you.
Thank you. Thank you. Bye.
Thank you. Bye.
Bye.